Hello guys, hope all of you are doing great. In this part of the video, we are going to learn how does backpropagation work. And we're going to learn it with the help of this very simple example, in fact, extremely simple example. Here we have this network, the entire network has only one neuron. And not only that, we want our network to learn only one example. There is only one training example, and we want our network to learn that training example only. That is, we don't want our network to learn any general thing. We want to learn only this specific training example, in the sense that whenever we give x equal to 0.32, we want our network to generate, say, the output y equal to 23. Okay. And there is another simplification I did here, that this neuron, if you see, it just takes the weighted sum of its input added with some bias. It doesn't make use of any nonlinear activation function that you typically see inside the neuron of a neural network. So, but anyhow, whatever it is that I'm going to discuss today, it is nothing is going to be changed if I add that activation nonlinear activation function here. Only thing is that it will become a bit more complex. Okay, and I'm keeping that complex part. So in my next videos, then certainly I'll show you examples where neuron contains nonlinear activation function also. But for today's discussions, for just to start with, just to know the basics of backpropagation, I mean, how it allows us to update the weights and biases so that we can train a network for desired output with respect to a specific input. We just want to see how things works there with this simple example. And once you understand this simple example, you can use the same concept to to more complex example. Okay, then having said so, now what we have is that we have a neural network where we have only two parameters. One is this W and one is this B, and we want our network to train for this specific example. And when I say train for this specific example, in the sense that we want our network to learn the right value of this W and right value of this. What is this W? What is the right value of this W? What is the right value of this B? So that whenever the input is 0.32, the output is 23. And that's what we say, the network has learned a thing. And the important point is, if you know how to train a network with only two parameters like 1W, 1B, the same process is basically involved in training a network which have like millions of weights and at least thousands of biases there. Okay, so the underlying concept is same, and that's why I have chosen this simple example. You'll learn all the details. You'll come to know it at the as you move forward. In this video. Okay, then let's now see the steps involved there. What are things that our neural network actually does, in this training process? Okay, so see, initially the network doesn't have any idea about what is this right weight, what is this right biases. So initially the network does the obvious thing. What it does is that it assumes this weight to be a random number. It just chose a random number, and that's this weight, and another random number for its biases. So if it has millions of weights and thousands of biases, then also it will do the same thing. It will just set all those millions of weights to some random numbers, all those thousands of biases to its to some random numbers. Okay. Here we have only two, so we set them. Say, for example, the random number chosen for W is 10, chosen for B is equal to 6. They could have been easily anything, any random number. Okay. Now, the network goes through three steps there. Like in a deep learning network, there are mainly three steps. One is this, like I'm saying three steps, but okay, let's see what are those three steps. So one is this forward pass. Okay, one is this forward pass, and in this forward pass, what the network does is basically it computes the output based on its current weight and current biases. So whatever it is, this W's and this B's, based on that, it will try to generate, and the given input, it will try to generate the its output there. So in this example, what it will do is it will simply take the output is equal to whatever it is the weight multiplied by this x, multiplied symbol and x look same. So multiplied by this x, and then it will add b to it, and whatever it is, that is the output. So in this case, specific example, suppose x is equal to 0.32, w is equal to 10. So 10 multiplied by 0.32 plus this 6, which is equal to 9.2. It is the the output generated by the network based on its current input, as well as its current weight and biases. Okay, done. Now, once the network does that, the second thing is that, okay, how good or bad this output is. We need we need a measure. There are two steps involved actually. One is forward pass, one is backward pass. Okay, so but anyhow, after the forward pass, what basically we are interested in seeing is that, okay, how good or bad this output generated by the network is. That is, we need a quantitative measure of how good or bad this output is, and that quantitative measure that we take to decide like how good bad this output is known as the cost function. Okay, the known as the cost function. It's a this cost function, it gives you a single number. It gives you a single number that says, like, that is the error of the network. Okay, and we want our cost function, we want our network to learn the parameters in such a way that the cost function usually goes to zero. The cost or the error of the network is usually zero. Now, see, based on the problem that you're trying to solve, this cost function can take, I mean, you can use different functions as cost functions. But here, let me tell you one thing, that whenever your network is producing some real numbers as output, as it is doing here, this is known as regression. And for regression problem, one very commonly used cost function is an effective cost function is this mean squared error cost function. And what does that mean squared error cost function do is, like, it subtracts the the desired output y from the generated output o, and it squares the difference. That is the the cost mean squared error cost function does. Okay, so for mathematical simplification, actually there is this half is there in front of it, but for the time being you can ignore it, no problem. Okay, so the cost basically is o minus y whole square. That's the cost. Okay, now see, the importance of this cost function is not only to tell you how good or bad the generated output is. This cost function it allows you to update the weights and biases in a systematic way. Okay, and from where this theory is coming up, that theory is coming up from the the well-known algorithm, which is known as the gradient descent algorithm. Now see, what does this gradient descent algorithm says you is that it allows you to tune the parameters of a function to find the optimal value of that function. And it means what? It allows you to move towards the optimal solution by taking small steps. If things are not very clear, don't worry. Now, this third statement should make sense to you. Okay. Now, see, if one is interested in this optimal solution, means what? It could be both finding the minimum or maximum. But suppose if one is interested in finding the minimum of a function, then the steps should be in the opposite direction of the gradient of the function with respect to the specific parameters. What I mean by this actually is, now see, quantitative measure is we have taken is this cost is equal to o minus y whole square. Now see what we want our network to do. You see here, if I plot the o versus cost value, this is your o and this is your cost, then what will happen is the cost will be 0 when o is exactly equal to y. You can see that if o equal to y, then cost will be 0. For any o value, any other o which is not equal to y, the cost will be a positive number. You can see that this is actually, it will look something like this. It will look something like this. Okay, so suppose, just assume that the output is 1 at some point of time, and this is a sorry, the output, what we want is, output one is I guess we want 23. Say the output is now, say for example 29. This is 23 is the right output. So at 23 we want the cost value to be 0. See here, 23 minus 23 whole squared is 0. So 23, it will be 0. But if it is 29, certainly it will have some positive error. But suppose the output is minus 29. It is at the same distance from the desired output, but in the negative direction. Then the cost will be the same because we are taking the square of it. Okay, so ultimately what we want our network to learn is, we want our network to minimize the value of this cost function. We want our network to produce the output, these outputs, in such a way that the value of the cost function becomes 0. That's what we want our network to do. And if it is the case, then we can make use of this gradient descent rule. Like if one is interested in finding the minimum, see, we want to find the minimum of the cost function, then the steps should be in the opposite direction of the gradient of the function with respect to, in the opposite direction means we are subtracting it, and the gradient of the function, that is rate of change of the cost function, with respect to a specific parameter. That is, we can update the, now see, you might be thinking this cost function is a function of O, how come it now is becoming a function of W and B? You can see that here, actually I have written it, cost is O minus Y whole square, so O is a function of W and B. So ultimately what is this cost function is? It is a function of ultimately W and B only. O is just a temporary result, an intermediate result, which is produced by this W and B. So ultimately, you can think of the cost is a function of W and B, and we want to minimize the cost. So if we want to minimize the cost, then what we have to do is we have to take steps in the negative direction of the of the slope of the cost function in that specific dimension, like dimension in the sense for that specific parameter. Now what I mean is, see, so if this is your cost function, then what we have to do is, if we want to update, or according to gradient descent, what we can do is that we can update the weights by subtracting here a constant fraction. Let me call it fraction, although it's not a fraction, actually it's just a constant number there, means that is the constant weight. Actually it's there, and it's a hyperparameter, don't worry about it. This parameter is not learned by the network, it's something that you specify from outside the network. Okay, so that term is known as the learning rate of the network. It basically says, like, this thing, the steps should be in the opposite direction. And when I say these steps, what should be the size of the step? Okay, whether you are taking a long step in each like iteration, or you're taking a small step in each iteration. So that step size is actually determined by this learning rate. Okay, and main point here is that we go in the opposite direction of the gradient of the function with respect to the specific parameter. So if we want to minimize cost, then we have to update these weight and biases, or in the sense that, or in other words, we have to go in the opposite direction of this, the slope of W and slope of B, so with respect to C. So what we're going to do is we are going to update the weight, like here I'm computing, this is the slope of the weight. See here, rate of change of the cost function with respect to the parameter W, and then we are subtracting a, we multiply it by a constant, and then that product we subtract from W. Why we are subtracting it? Because we want to go in the opposite direction of the slope of the function. So if this slope is positive, then we are subtracting it. If this slope is negative, then that minus will be multiplied with this minus. So basically we will be increasing the value of W. Okay, although it's a minus symbol, don't you think that W is always decreased? It might happen that the slope is negative. In that time we have to increase the value of W, and the same is true for these biases also. Okay, got it. Now this is these two terms that I wrote, W equal to W minus eta into rate of change of cost with respect to W, rate of change of cost with respect to bias, they're coming directly from gradient descent. Okay, now that's okay, fine. But the next term is that how do you know what is the cost of the function, or what is the slope of the function, sorry, what is the slope of the cost function with respect to W, and what is the slope of the cost function with respect to B? If we know how to calculate that, then a problem is solved, right? Now let's try to compute that rate of change of the cost function with respect to W. How do you do that? Let's see this neural network that we are trying to learn, trying to train. This is your X that goes that is multiplied by some W, and then there is this bias term, and then we take WX plus B, and that is your output actually, right? And this output, and then we have this another term there, constant term Y, constant in the sense this output is not changing. Our desired output is always fixed, so that in that sense Y is a constant. From this O generated output and Y, we compute the cost in this way. Cost is equal to O minus Y whole squared. That is our cost. Now see, if we now want to compute the rate of change of the cost function, that is, we want to find how much this cost will change if we do a small change in this W. And at the same time, we want to compute how much this cost will change if we do a small change in this B. So how do you do that actually? See, this cost is not directly, is a function of W. Rather, it is a function of an intermediate result O, which is again in turn a function of W. So we can write this equation, this term, rate of change of the cost with respect to W. We can split it into two parts like this. Rate of change of the cost function with respect to this output. That is, first we decide like how much this cost changes when we do a small change in this output, and then we multiply that thing with how much this output changes, when we do a small change in this W. That's all. Now see, this is known as the chain rule. This is known as the chain rule of partial derivatives. Now, even if you do not know chain rule and all, then you can see from here is that this dou O and dou O, that they will get cancelled, and ultimately what we'll have is dou C by dou W, right? So that's what we are computing. Now, writing this term dou C by dou W in this way, or as a product of two terms, is quite useful, because now we can find the derivative. Now we know like what is the rate of change of the cost function with respect to O, where the cost function is written in terms of O minus y whole square. So that is this term. Okay, rate of change of the cost with respect to O means ultimately we want to find what is the rate of change of O minus y whole square with respect to O. Okay, and this other term multiplied by rate of change of the output with respect to W means rate of change of the output with respect to W. But what is this output in terms of W? Output in terms of W is Wx plus B. Wx plus B. Now, if you know the rule of differentiation, then these terms are quite easy to find, figure out, like what is the rate of change of O minus y whole squared, where y is a constant with respect to O, is nothing but twice these O minus y. Okay, and that's why I said you that the cost function, actual cost function, has a half in front of it. And if we have that half in front of it, then this half will cancel this 2. So it will be only O minus y. But that is only for some mathematical convenience. Okay, that's all. So directly we can ignore that 2 without any problem. Okay, so mathematics support that thing. You don't need to worry about it. So 2 minus O minus 2 into O minus y multiplied by what is the rate of change of this term with respect to W. Now you see here, this term, it is like this B doesn't change, like the rate of change of B with respect to W is certainly 0. B doesn't depend on W, so obviously it doesn't change. I mean, no matter what you do with this W, B is not going to have any effect of, B will not have any effect, right? So rate of change of B with respect to W is 0, but rate of change of Wx with respect to W is x. So you have to multiply this term with x. And as I said, no, using some mathematical trick, you can cancel out these two and you can ignore these two. So ultimately, rate of change of the cost function with respect to W is equal to O minus y, whatever the output we generate, minus whatever it is the output that we need, multiply that thing with the input x. That's all. So that is the rate of change of the cost with respect to W. This first term you will be computing in this way. Now, if I ask you what is now then rate of change of cost with respect to B, then you will do it very easily. Then you see here, it is the same thing here. How much the cost function changes with respect to O, and then how much this O changes now with respect to B. Okay, so that's what we're going to do. How much this cost changes with respect to O, which is same as the first term is same, cost with respect to O, which is 2 into O minus y. Directly you can write that. And then how much this cost function changes with respect to B. So this term we already know, it is 2 into O minus y that we have computed, then multiplied by rate of change of the cost function, which is Wx plus B. In terms of B I have written, and then B. Now if you see this thing, Wx, certainly there is no change of Wx if you do some change in B. So rate of change of Wx with respect to B is 0, but rate of change of B with respect to B is 1. Like if you increase, it will also increase. If you decrease, it will also decrease linearly. And so it means this term is turned out to be 1. So it is like 2 into O minus y multiplied by this term, rate of change of Wx plus B with respect to B is 1. So ultimately, rate of change of cost with respect to bias is equal to 2 into O minus y. And again, as I said, no, using this mathematical trick, you can omit this 2. So ultimately, it is O minus y. Clear? Okay, done. Now we know what is the rate of, now this is another term here. we have computed. So done. Now we know like what is this rate of change of cost with respect to W, rate of change of cost with respect to B. So once we have those values, and eta, as I said, no, it's a learning rate, it's a hyperparameter, it will be specified from outside at the beginning itself. So this value we know, W, the previous weight we know. So we are now ready to compute then the new weight. So what we have to do is just take the old weight from there, subtract eta into whatever this dc by dw, we'll get the new weight. And same thing we can do with this B also. So that's all then. That is known as the back propagation. So let me summarize everything now. So what we do is we have some X. This is your training example. Okay, let me write all the steps. Now it will give you a clear picture. This is your training example. Say for example, X is equal to, I guess it was 0.32 or whatever it is. Then we also have some, training. This is a training X. This is a training Y, the desired output, say for example, 23. Then we have some learning rate fixed eta, say for example 0.1, and also we have another term I'll show you. Along with that, we have some random weights, say for example 10, and random biases, say for example 6. These are random numbers. Okay, these are random numbers there. This is also random. You can start with anything, 10, 6, or -5, -6, or whatever it is that you want. And then once we have that, what we want our network to do is we want our network to do is a forward pass. Now in forward pass, what the network will do is it will simply generate the output based on the current weight and current biases. So it will do something like this. So whatever it is the current weight multiplied by this X plus whatever it is the current bias, that is our output. That's done. Once the forward pass is done, then we want to do a backward pass. Okay, a back pass, that is known as the back propagation. So in backward pass, what we do is we compute these terms. Now, what is the rate of change of the cost function with respect to all the parameters in our network? See, if in our network we have only these two parameters, W and B, and we do this WX plus B simple operation, and we generate this output. So we have to compute the rate of change of the cost, and from this output and this Y, we have this cost function. So in a neural network, in the back propagation, what we have to do is we have to compute the rate of change of the cost function with respect to all the weights and all the biases. So you have only one weight here, so we'll be computing it. Rate of change of the cost function with respect to dw is equal to, it turned out to be whatever it is, O minus Y multiplied by this input X with respect to W. Okay, and let's call it, like, for simplicity, it is DC, simply DC. Okay, sorry, not simply DC, let's say simply dw. And similarly, we'll be computing the rate of change of the cost function with respect to B. That turns out to be O minus Y multiplied by 1, so O minus Y only. Done. This is your, in back propagation, first we'll be computing this gradient. These are called as the gradients of the parameters, and then in the back propagation itself, another step that we'll take is, the final step is update the weights and biases. Once these gradients are computed, updating is very straightforward. It is whatever now the new weight will be, as many weights you have to do for all of them. The new weight will be the previous weight minus this learning rate eta. What did I write eta as? Eta as eta. So let me write here for time being, eta as eta multiplied by this rate of change of W with respect to dw. That I wrote only by these terms, dw. Okay, that's the error. And similarly, we'll update B by whatever it is B minus that eta value multiplied by rate of change of the cost function with respect to B. In this case, I'm writing it by this symbol dB. And that's done. We update these W and B. It means, see here, after updation, our weights and biases changes. It means what? It means with these new weights and biases, we'll get a new output there, right? And again, if you have a new output, then with respect to that output, again, the derivative of W and B will change. And from those derivative, again, we can compute new weights and biases, and we can repeat this process. See here, usually this process, this forward pass and this backward pass thing, this forward and backward pass, this forward and back, these two steps will be repeated. Like once this WNB, new WNB is calculated, the process will go back to this forward pass once again, and again it will compute the new output, and again it will do this back propagation, again it will update the weights and biases, again it will go and it will compute the new output, and this process will be repeated. And how many times this process will be repeated, it is again defined by another hyperparameter which we call as number of epochs. See here, if you have any experience with deep learning, and if you have started learning it, then you might have heard these terms like epochs, the back propagation, updating the weights and biases, forward pass. And in this simple example itself, you can see all those terms coming up. Not only that, you can see this learning rate term also. This eta, as I said, no, it's the step size, like how big or small your step size is, and that is known as the learning rate. So this epoch, let me write here now, this epoch here. This is another another hyperparameter that we have to specify if you want to train the network. So let's say, for example, 10, 20, 30, 100, 1000. It could be anything. Okay. Okay, then. So that's these are the steps which you need to follow if you want to train this simple network for one specific training example. Say whenever it is 0.32, your network you want your network to generate 23. So these steps if you take, then at some point of time it will learn the right weight and right bias to map 0.23 to 32 or whatever it is. Okay. So once you people have understood this thing, now it is time to write some code and verify our understanding. Okay, then let's see. Okay, now I'm in Google Colab Notebook, and I'm using this NumPy library. Now for any scientific computation, you can use this. NumPy is quite useful for doing this scientific computation. Okay, so I'm using NumPy. And then let's now do our neural network thing. So what are things that we need to initially have? So we have this X, which is our training example, the X. So you can say like X, okay, let's call it X. And say, for example, it is 0.32. And this is your, test, the level of Y. Y is equal to what we want. We want Y to be 23, okay? Done. Once we have that, we also have some hyperparameter. Let's fix this. Eta, the learning rate or the step size, is equal to, say, for example, 0.1. You might be thinking, from where did I get it? Usually it works with 0.1 or 0.01 or even 1. But it is, again, I'm saying this is a hyperparameter. You have to set it by yourself, and it comes with some heuristic. Okay, so maybe you can like see what other people who have solved the same problem that you are currently working on, and they have used the learning rate as, and accordingly you can set it. There are different ways, but for the time being, I think 0.1 will be, will be sufficient. And we'll once the code is written, we'll try to change this value, and we'll see what is the effect of this learning rate. I mean, can we take any random value, or is it like, we have to take some meaningful values? That question I'll try to answer at the end of this, or towards the end of the video. Okay. So then again, this number of epochs, and again, it's a hyperparameter. Initially, you don't know how many epochs you'll be needing. So you just start with some value, and then as you proceed, you will automatically get ideas to adjust this hyperparameter. It's like number of times you want to repeat the loop, and you can repeat the loop as long as you are not satisfied with the the cost of the function, or as long as the cost is above some threshold. Then you can ask your network to learn more and more. Like if it is below some threshold, then it's okay, that is tolerable, so you can stop, something like that. Okay, now these are two hyperparameters we have this input. This is sort of like training example. These are the hyperparameters. Now the parameters of the network. So for that simple example, we have only two parameters, W, and as I said, now you have to start with some random value. So I'll be using numpy dot random rand, and say within the range of 0 to 1. But for the time being, what I'll do is that I'll be using that same number that I showed you in the example. Later on, I'll replace it with this random function. But for the time being, say W is equal to 10 and B is equal to 6. Let's start with that. Okay, done. These are two initial values of weights and biases. Now we have to do this forward pass. Okay, forward pass. And in forward pass, what we want to do is we want our network to compute the output, that is compute all. If it is a very deep network, then we want to compute the the output at each layer, and at the end the final layer. But here only we have only one neuron, so no need to worry much about it. So output is simple. Output is equal to whatever it is, w multiplied by x plus this bias, and that's our output. Okay, now let's for the time being print this output on the screen. Say okay, I'll be printing it later, don't mind. The output we have generated, that is our forward pass done. In just one line, forward pass is done. Now it is time to do our backward pass or back propagation. Now let's put your focus here. This is back prop. Okay, now in backprop, what is the first thing that we have to do? We have to compute the gradient of the cost function with respect to our parameters. That is, say rate of change of the cost function with respect to dw. So with respect to w, let's call it dw. Okay, so dw means it is, let me write here, rate of change of cost function, let me write it as only cost with respect to w, with respect to w. That's what dw is. So dw is equal to, now we have computed it actually. If we use the cost function as o minus y whole squared, o minus y whole squared by 2, then dw is, or the rate of change of cost with respect to w is o minus y into x. That's what we have computed. So let's directly write it. It is o minus y into x. So whatever it is o minus whatever it is y multiplied by whatever it is x. X means the input. Okay, so that's done. Now similarly, we'll be computing now what is the rate of change of the cost function with respect to b. Rate of with respect to b. Let's call it db, and it is, we know that this x is replaced by 1 there. Okay, so that you can see from here, rate of change of cost with respect to b is only o minus y multiplied by 1 is there. Okay, now once we have that, we know like the derivative, then we'll be using the concept of gradient descent. That is, we want to find the optimum solution or the minimum. Then what we have to do is we have to move towards the opposite direction of the gradient. And how do we do that? We'll update our weight. This is your update operation. Okay, update weights. So update weights and update parameters, basically update parameters. You have to update all the weights and biases. Maybe there are millions of weights, thousands of biases, or maybe there are only one weight, one biases, but you have to do that. W will be whatever it is the previous value of w. From there you will subtract. We will subtract because we want to go to the in the negative direction of the slope. So w minus that eta, that learning rate, multiplied by whatever it is the rate of change of the function with respect to that particular parameter. So we are updating w, so we have to make use of the rate of change with respect to w. That's all. Similarly, b is equal to same b minus eta, whatever the same eta, the same learning rate, multiplied by rate of change of the cost function with respect to b. That's all. We have updated our weights. Done. Now the next thing is that we have to repeat this process. Since we have now a new weight and slightly modified version of the weight and biases, then we can use that modified w and b to compute again the output, ask the neuron, ask the network to produce the output, see how good or bad it is, and accordingly you just repeat this process, okay, as many times as you want. And or you can say like as many times as specified in this number of epochs. Okay, so if we want to put, basically what we want to do is now we want to put a loop around this forward pass and backward pass there. So here, not here, not here, here from this forward pass thing. Okay, so we want to put it in a loop for I in, say for example, range, within a range of 0 to epoch, epoch, epoch. I guess the spelling I have written right. Is it right? Yes. Okay, 0 to epoch. Then we want to repeat this process, do the forward pass, update the weights, and that's all. And that's all. Then in each iteration, say we want to split print out, like print what is the current output. So output or let me write here o equal to, and concatenate it with the string version of the o. This is just for printing, don't worry. Plus then what is that cost? I want to see the cost is equal to, plus convert the cost string and print it. Where is my cost? I have not computed cost here, but I have to see. Computing the cost is right now only to see like what is the cost, but we have used cost there to update the weight and biases, and that's where this term is coming, O minus Y. This O minus Y is actually the rate of change of the cost function with respect to O. You remember it? So that's where it is. Okay, but if we want to see explicitly what is the cost, then we can compute the cost here. I mean, that cost is actually, for this iteration, cost was O minus, this is your O minus whatever it is, this Y, and you take the square of it. That was the cost actually. That was the cost. Okay, and we want to print the cost on the screen. That's why I computed the cost also, and it'll print the cost on the screen. Now let's run this program and see the output there. Okay, our learning rate, all these things are done, and I guess you will have understood the concepts also. Let's run it and see the output. Okay, now see what happens. Did I import numpy? Okay, great. Now see, the first iteration, it was 9.2, and the cost is around 190. That is O minus Y. Y is, see, O is 9.2, Y was 23, so 9.2 minus 23 is now approximately 13, 169, 70, 190 approximately. Okay, you can compute it actually. The cost is 190. In the next iteration, and after the cost is computed, we updated this weight and biases also according to this formula. And see, in the next iteration, the output is slightly increased, because you see, we want our output to be 23. So from 9.2, it has moved towards the output, desired output, and immediately the cost, you can see it has gone down there. Got it? So at the end of the 10th iteration, the output, it reached up to 18, not yet this this desired output 23, but it is moving towards it. That's the hope. And cost is also, you can see it from 190, it has reduced. Like in each iteration, you can see that the cost is going down and the output is sort of moving towards the desired output. Only problem here is that we have terminated the program. This number of epochs is not sufficient to for the network to actually reach the optimal solution. So for that, just increase the number of epochs. Like say, instead of writing 10 there, let's run 100 times, repeat the same process. And this time, after 100 iteration, you can see now the output has reached to 22.999. For many practical examples, I guess 22.999 you can consider as 23. And the error, you can see it is like 1.7, 10 to the power minus 8. It is an extremely small error there. So you can say that at this point, the network has learned properly, the weights and biases, for which, for this training example, that is whenever you give 3.32, it knows how to map it to 23. Now see, this training example doesn't have any specific. That pair I just chosen randomly. It could be anything. So for example, for x is equal to 0.45, we want the output to be, again, a decimal number. Say for example, it is 0.09 or something. Okay, so let's see if I run this program, and at the end directly you can go, it is like 0.09. Is it the thing that we want? We want 0.09, right? So that's what it has learned. So the output is towards the end, it is 0.09003, which is almost equal to 0.09, and the cost is 1.410 to the power minus 9. Very small error there. Okay, so it could have been anything actually. It's like 0.45, and I want this thing to go to 1. That is also possible. The same code, we are not changing anything about the code, and you can see it's now going to 1 there, right? Now let's do something with this. Now epoch, you have understood, right, why this epoch is important. That epoch means how many iterations you want to you want your network to repeat that loop, and certainly you have to give it enough number of times so that it can do that forward backward sufficient number of times, so that the weights and biases are adjusted properly. So epoch, certainly you just want to keep it enough, right? More you give, better it is. Obviously at some point of time it might not the cost might not go down any further, so at that time certainly you can stop it. But the thing is that if you give it more, it will not harm anything like in terms of your output. But what about this eta? I mean, okay, let's this eta, as I said, no, it's like intuitively it is the step size. Like suppose you just assume that you are at a mountain there, and you want to go to the the valley of the mountain, and you take a step. Like how big your step size is, that is actually determined by this eta. Now suppose right now eta is 0.1. Now suppose I just want to reduce the step size by 10. It means I want to take a small step size there. Okay, so it means what will happen, what intuitively what will happen if I reduce the step size? It means to reach that solution, it will take me more number of epochs, right? In each epoch we are updating the weights and biases. That is, in each epoch we are taking one step. So if we are taking a smaller step, then certainly in 100 epoch we might not reach that solution, because we are now taking a smaller step, right? So that's what you can actually see, I guess. Like, let me see what happens with 0.1 output. You can see now this output is 3.86 and the cost is 8.22. It's like far away from 0, and the output we wanted was 1. And what output we are getting is, we are getting this output as like 3.86, although it is reducing. You see, 4.4333, cost is also coming down, but it is not the right solution. Why? Because it is the same number of epochs you have used, but only thing is that we have this small step size there, right? So in this case, you might want to increase your epochs, then you will get more or less the same output there. You will get more or less the same output 1, and then this, it's okay, fine. Or what you can do is you can increase this step size. So if I now increase it like to 1, and so 0.1, now it is 1, and 1000 epoch I'll not be using. I'll be using only 10 epochs there. Let's see what is the effect there. Okay, so now I'm taking big steps. So if I take big steps with less number of epochs, I can expect to reach the valley of that mountain. And see, with just 10 epochs, we want our output to be 1, and it is 0.999999. Any practical thing you can say, like that's 1 almost, and the cost is 2 into 10 to the power minus 11, which is like almost 0. So that might give you the impression that, okay, then I can just write eta, the step size, to be too big. Just in just one single epoch I reach this valley. That is not the case always. Okay, greediness is not always good, huh? So you just now change this thing to 10 then, and let's see what happens there. If I run this program, this epoch actually plays an important role. And see, now this time suddenly it is output is minus 0.22. Where is my output? I started with 10, then it is becoming minus 10, then sometimes it is too big, then again it is in the negative direction, too big. You can see now it is oscillating from one point to another point. It is not moving steadily. It is as if what you are doing is, actually, you can think of intuitively, is that you have this bowl, right? This is your O, this is your output, and this is your cost, and this step size is like how much you want. This is not directly in terms of if you take bigger step size, then what is happening is that you might miss this minimum point. So from here directly you have reduced X and B, so that or you have changed this W and B such that next time when you compute this cost, it is somewhere here. Okay, it just crossed that minimum value, it landed up here. And again, because of your large step size, next time when you update weights and biases, instead of moving closer to this W, you might actually shoot up here. Then next time you might shoot up here. Next time again you might shoot up here, maybe somewhere close again, but somewhere bigger, far away. Sometimes it might just go out of this picture, like it's like a randomly big number, or randomly small number, like that, might happen. So this eta value, it plays a very crucial role there. You just cannot set it to any random value and expect the network to work. Okay, so if you don't know anything about eta, and you're like, you just want to start with something, then you just start it with some very small value, say for example 0.01 or 0.001. So that will see here, although in the first go, suppose I set it to 0.001, although in the first go we do not get the output, but it will give you an idea. You see here from 10.5 it has moved to 10.39, and the cost is also reduced by some amount. Then you can increase the number of epochs to some degree, and you can see where it is going. Is it going in the right direction or not? Is it moving towards the minimum or not? Okay, and if you see that, okay, this epoch has minimum, but the thing is that it is unnecessarily taking some small steps. Now you're confident that you can slightly increase the step size. So once you have that confidence, then you can slightly increase the step size, and if you still get some stable behavior, then you will get more confidence, and then accordingly you can update the this learning rate. But I guess for default one, it is 0.01 or 0.1 and 0.001. All of them will work fine. Okay guys, then I hope people have understood the concepts which are involved in a neural networks training phase, mainly the backpropagation algorithm, and how do we compute the partial derivatives, and then we use those partial derivatives to update the weights and biases in the backprop in the training process. Okay, so that was my main point. Like that's what I wanted to convey through this video. Certainly, my example was very simple. So in my next part of the video, what I'll do is I'll try to solve one slightly complicated example where I will include in the neuron, like I'll be using a more realistic neuron, or a neuron which we use in our typical deep learning models, where the neuron or most of the times the neuron has this non-linear activation function after this summation step. That is, what we want our neuron to do is we want our neuron to take the weighted sum of the input, that sum, let's call it say z, that temporary result, the weighted sum, and then we want this neuron to pass this weighted sum through some non-linear function, and whatever it is the output of that non-linear function, that we want our neuron to produce as an output. Now we'll be seeing two different types of nonlinear function, like ReLU and sigmoid. If we use ReLU, what should be, see here, our ultimate goal, in this entire process, one thing you should know is that everything is same. Like initially it will be computing the output with respect to this W and B, and if you know what it is, this nonlinear function, computing the output is quite straightforward. In the backpropagation, then how do you update the weights and biases? Ultimate question is how much the cost function changes with respect to dw, and how much the cost function changes with respect to b. These are two questions you have to answer for this network also. But here the trick is that the output is not directly dependent on now b or w. Now output depends on z, and then z depends on this w and b. So there is one more link there in this chain rule, in this chain of partial derivative. There is this another link there, and that's what we're going to see in the next part of the video. So if you have liked this video, now if you have enjoyed, or if you have learned something from this video, please press the like button. It will help my channel to grow, and it will certainly motivate me to create more videos like this. And also, if you're interested in the coming videos, which I'm planning to do, like plenty of machine learning, deep learning type videos there. So if you're interested in such videos, then you can subscribe the channel also. Okay guys, then that much only in this part of the video. See you guys with this new content in the next video. Till then, have a nice day.